Log on, tune in, find out. Another good idea from Cambridge.
Show you how to write down the functor which induces the derived equivalence, a construction which is due to Rickard, and then say a bit about the ideas that go into the proof. And then in the end, if I have some time, I'll say how this this derived equivalence could be included in a family of equivalences which are in a way just a sort of combinatorial type of an equivalence. Okay, so let me just remind you what an sl2 categorification is. Okay, it's a abelian category which is k-linear for some field k, and we make some assumptions on A. For example, it has composition series. And we have a pair of exact functors from the category to itself, and we assume that there's an injunction in both directions. And importantly, for it to be related to sl2, these on the Grothendieck group will induce an action of sl2 through the usual Chevrolet generators. So on the Grothendieck group, okay, we further assume that there's some decomposition of the abelian category into a direct sum, which corresponds to the decomposition into weight spaces for the sl2 action. Okay, and finally, and most interestingly, we have the action of degenerate affine Hecke algebra on powers of the functor E. So we have action of compatible actions of affine Hecke algebras on powers of the functor. And the goal of the whole setup is to lift the action of a certain automorphism of the Grothendieck group, okay, given by an exponential formula, which I'll write out here. Okay, here I'm using the brackets to denote a divided power. To an automorphism of the derived category. So in the definition I gave yesterday, these actions were given by operators x and t on E and its square. And those locally are generators for the action of this affine Hecke algebra when you take powers. Okay, I've been a bit sloppy about saying whether my Hecke algebra is degenerate or non-degenerate. And I suppose the reason is it doesn't really matter. So that's a remark that by this I mean either the degenerate or the usual and in fact Ruki has shown that you can have an action of the nil-Hecke algebra as well, and you get the same picture. So the advantage of the nil-Hecke algebra is that it's graded, it has a nice grading, and so I suppose that therefore one should really be talking about abelian categories equipped with a grading, and one would hope that the same result would go through. And in fact, a particular instance of this has been carried out with a slightly different set of axioms, and that's work of Kottis, Kamnitzer, and Licata. Okay, and a big difference in their setting, which comes in the geometry, is that their functors aren't acting on, well, they have some non-exact functors on some category of sheaves. So really, they only get the induced action of sl2 once they derive the functors. Another way to say it is that their general setup works for functors which are acting on a triangulated category. Okay. So here I assumed that we had exact functors on the abelian category, and we got an equivalence on the derived category. But they set it up in a more general setting where they just have a triangulated category. Okay, and we may hear also from Ruki next week that his setup works in this kind of generality as well. Okay, so let's go about now to construct this lifting. Okay, so we want to take this formula as the guide for what to do. And the first matter of business is to understand how to categorify this divided power. Okay, so we know that we should just capitalize the letters there, and that should be about it. But interpreting what this capitalization means is the rub. So the first thing is, as I said, the divided power. So what do we mean by e to the n divided by n factorial? Okay, that means we want to split this functor into a direct sum of copies of a single functor. And to do that, we need the action of the degenerate affine Hecke algebra. Okay, so remember that inside this algebra, which is generated by a bunch of t's and x's, if we take the subalgebra generated just by the t's, we get a group algebra symmetric group. Okay, and inside here we can take a symmetrizer, something which we saw in Rune's lecture this morning. So we can take the sum of all the group elements. Okay, and let's call this Cn. Okay, and we can then just symmetrize e to the n. Okay, this is an endomorphism of e to the n, so we just take the image of the endomorphism. So we define the divided power to be this image. Okay, as it turns out, we're going to need two versions of this divided power where we just take the anti-symmetrizer as well. So if we include the sign representation, then we can define an analogous subfunctor. And I indicate the difference by putting a minus sign there. Okay, it will turn out that these are isomorphic functors, but for the construction of the complex, it's important that they're not equal submodules of the big guy, e to the n. Okay, and of course, the first matter of business is to prove that this is indeed, this should indeed be viewed as the correct notion of divided power. We need to show that this is a lifting of the divided power on the Grothendieck group. And of course, that's just a statement that that e to the n is, in fact, the direct sum of n factorial copies of the putative derived divided power. Okay, and the proof goes like this. We start with the submodule or subfunctor inside here. And that was obtained by symmetrizing by the action of the symmetric group. Okay, now we want to use endomorphisms of e to the n, namely the bit that we know, which is the affine degenerate affine Hecke algebra, to move this copy to get the other summands. Okay. Of course, we can't use the symmetric group anymore because the symmetric group fixes this symmetrized bit. So we have to use the x's. And so we take various powers of the x's. And we find that we get a direct sum this way. Okay, and indeed, each of these pieces is isomorphic to e to the n. And I suppose to actually prove this, we really are, one really has to appeal to the representation theory of a small part of the representation theory of the degenerate affine Hecke algebra. I'm sorry? Oh, yes, sorry. Yes. Thank you. Thanks. Yeah. I'm sorry? The J, sorry, it's just the index for each of the, so so I'm taking the sum over all tuples, I suppose. And I'm taking the sum over all tuples I1 through IN, satisfying this condition. Yes, that's right. So there's n factorial factors in this. So the idea goes as follows. We know that the, I mean, I guess I didn't include all of the assumptions here, but in this action of HNF on e to the n, the x's are supposed to act nilpotently. So we can just really use a part of the representation theory, which for which that's true. And here, there's only going to be a unique simple module. So in this unique simple module, as a module over the symmetric group, is a free module of rank 1. So when we take the symmetrizer, we just project onto the fixed points. Okay, but since this module is irreducible, one has to be able to use the other operators to build up the whole module again, and one does it in this way. Okay, of course, the same thing is going to be true for the negative version. I suppose I should also say that in the axioms, I only assumed an action of the degenerate affine Hecke algebra on e to the n, but through the adjunction, I can move the action over to powers of f. Okay, so maybe I should say that if we fix some adjunction between e and f, then that gives me an isomorphism between the endomorphism ring of natural transformations of e to itself, or even e to the n to itself. Okay, with the corresponding endomorphism ring for the adjoint, up to changing the order of the multiplication. So an action, so from this we get an action of the affine Hecke algebra also on f to the n as well. So anything we do with e, we can do with f. In particular, defining divided powers. Okay, so now we know how to capitalize the e's and f's here with the divided powers. And so we have something which looks like the terms of some complex. Okay, but that, well, at least I don't know how to write down a suitable complex having terms which involve those guys. Okay, but what Rickard did was, not in this language, but essentially, is restrict to a weight space. And the formula becomes easier when you do that. Okay, so, sorry, maybe before I do that, let me say one thing about one consequence of this existence of divided powers, is that one of the examples we saw, so recall that we had an example in the previous lecture, okay, where we put, we were categorifying the three-dimensional irreducible module, and we had the category of vector spaces in the middle, and then on the ends we had modules over k of x modulo x squared. Okay, and the functors e and f were given by induction and restriction functors. Okay, so this was a mild variation on example 2, where the roles of k mod and k of x modulo x squared mod were interchanged. Okay, example 2 is a sl2 categorification in the sense that one can define the action of the affine Hecke algebras and so forth. But this one is not, and one way we can see that is that if you take e squared, okay, you get a functor from k of x modulo x squared to itself, okay, and you can easily check that this is indecomposable. Okay, which would contradict the existence of the divided power, right? This should divide as a direct sum of two guys. So that means that we cannot introduce the action of the affine Hecke algebra here. so now let's construct the complex of functors, which is going to induce the derived equivalence. Okay, as I said, the formula for theta on the Grothendieck group was this triple sum. But once we restrict, we can get something easier. Let's restrict to the weight space of minus lambda. Okay. Then we just have a single sum minus 1 to the d divided power e lambda plus d and f to the d. Okay, so this takes the weight space of minus lambda to the weight space of lambda. Okay, so we're going to try to lift this guy. So we're going to define. Okay, so let's just try to lift the action on this weight space. So we'll call this is going to be a summand of our final functor. Okay, so we're going to index it by lambda. Okay, so the terms are just given by capitalizing the summands of the easier formula. Okay, so the dth term is going to be e, a divided power of e times divided power of f, now viewed as functors. And okay, I'm going to write it as a chain complex instead of a cochain complex, I suppose. And the next term is then going to be this guy here. Okay, and we have to define, of course, the differential. Okay, so these were defined as subthings of powers of functors before they were divided. Okay, so of course the only difference between these two guys is that here I've stuck in an extra, I can think of it as sticking an extra e and f in the middle here. Okay, so to get from here to here, I'm going to need a map from EF to the identity functor. Okay, and of course that's where the adjunction comes in. We can take the co-unit for the adjunction. Okay, and use that to build the map here. Let's call this epsilon. Now, you have to fix an adjunction to actually write down the complex. And of course, you have to make sure that this adjunction is the same one that you used to relate the actions of the degenerate affine Hecke algebra on E and F, or else this complex isn't going to work out. I mean, it's not going to even be, this map won't even be defined, you see, because this one needs to be able to restrict. Oh, actually, I think this part is fine. Yeah, I mean, it's easy to check that this thing actually restricts to these divided powers. Okay, and then okay, then the theorem that we get. Okay, and for the sake of being able to refer to it, let me just call it theorem A. That it's bounded. It's going to be, I suppose, locally. Yeah, in fact, maybe it's not bounded. It might only be locally bounded. I mean, it might be what should I say? It's a. Let me think. That's right. Yes, that's right. Yes, I guess if I assume that the sl2 representation is finite dimensional, that's certainly fine. But would it be okay for a locally finite one as well? No, I suppose you're right. Yes, if we just fix. Yeah, if we fix some object, then by the local finiteness, we're going to get only finitely many terms. So the image will indeed be bounded as well. Yeah. And of course, the same argument will apply to any bounded complex. Okay, so the first thing to check is that this indeed defines a complex, namely the square of that differential is 0. Okay, and that's not true the way I've done it. To get this to work out, you need to use the other version of the divided power for one of the two functors in the pair. So this was the trick that Ricard used. So here we use the negative version, the alternating version of the divided power. Okay, and having done that, you get this essentially because if you multiply C2 with C minus 2, you get 0. Okay, and as expected, we get the desired equivalence of derived categories, which relate opposite weight spaces. And then taking the sum over all these restrictions, we indeed get an equivalence which lifts the action of theta. Yeah, I suppose that we need this. I'm defining this functor between categories of complexes using a complex of functors. Okay, so if I don't have, if this is not a complex to begin with, then it's not going to define a functor for us. Okay, so now I'm going to explain some reduction steps that one takes to prove this result. Okay, so we can try to look at the representation theory of sl2 to give us a hint, again, as to what to do. So we use the fact that it's semi-simple to decompose the module. Okay, so V is the Grothendieck group. To decompose it into its isotypic components. Okay, so we denote by V to the Vn the sum of the irreducible submodules of V of dimension n+1. Okay, and ideally we would want it to just lift directly to the abelian category, right? So okay, but as we already saw in an example, this decomposition does not lift. Okay. I think it was example 5. Okay, there was an example involving blocks of symmetric groups where on the level of the Grothendieck group we had a direct sum of 2 irreducible SL2 modules, one of dimension 2 and the other of dimension 4. And these were all blocks, so there's no way that you could have a decomposition like this. Okay, but we can still do something with filtrations. Okay, instead, we consider the filtration on any SL2 module. Okay, given by taking V less than or equal to n to be the sum of all irreducible submodules of dimension at most n+1. Okay, so in effect, we're taking the sum of all of these VI's. Okay, and this is a good way to do it. Does lift to a nice thing for the abelian category. And here I define these lifts in the most obvious and crude way possible. So I just take the less than or equal to n category to be the set of all objects whose class is contained in the Grothendieck group version. And so what do I mean that this is nice? This lifting is nice. I mean that these are nice subcategories. Okay, they're categories which are closed under the usual operations that one can think of in the abelian category, taking of subobjects, quotients, or extensions. Okay, and this is not entirely obvious. One has to use some integrality properties of some positivity properties of the representation. Okay, the fact that these the fact that the functors have to take objects to objects and not negative objects imposes some positivity, which allows you to prove this. Okay, so let me just set that down. These parts of this filtration are Sear subcategories. Okay, and the good thing about sl subcategory is that you can take the quotient by it and get an abelian category. Okay, so we define, we consider these quotients. Okay, and the first reduction step is that we can reduce the theorem A to the case where we're just working with these quotients. Okay. So the idea is that the sl2, the structure of a sl2 categorification on A restricts to an sl2 categorification on these sl subcategories, and then also passes to the quotients as well. And that amounts to a reduction to the case where the sl2 module is isotypic. Okay, in that situation, one can strengthen theorem A. Okay, in that one essentially gets not just derived equivalences, but equivalences of the actual abelian categories. Okay, so let's suppose now that is isotypic. It's a sum of just copies of a single irreducible module. And let's just say the dimension is n+1. Okay, then this complex of functors defined by Rickard. Okay, when we restrict it to a weight space, it has homology concentrated in a single degree. Which is given by the formula n minus lambda divided by 2. Okay, and then this homology is now just a functor on the abelian between the abelian categories, or from the abelian category to itself, and this is going to be an equivalence. Okay. And that homology induces a derived equivalence between the, or rather an equivalence between the categories. Okay, so that means the original complex should be regarded as just something like a shift. Once we make this identification, then this is just shift by m. So once we reduce to this isotypic case, it doesn't look that interesting. It's just essentially an equivalence of abelian categories shifted by m. Okay, but the important thing, this doesn't mean, however, that for an arbitrary representation, that we're just getting a equivalence of abelian categories, because these shifts can change depending on which part of the filtration you're at. Okay. And if I have time, I'll say something a bit about this sort of derived equivalence, which is filtered by shifted equivalences of the abelian categories. Yeah.
So define the function theta to be a complex of functors. So doesn't it preserve degree somehow anyway?
Yes. So sorry, what's the? Oh, you mean what do I mean by shift by m?
Yeah.
Okay, so I suppose what I mean is once I identify these two abelian categories. Okay, so let's just suppose they're both that I just call it B or something. Okay, so we have here a functor from the derived category B to itself. Okay, I'm saying that this functor is just the translation.
Oh, I see.
Yeah. In fact, one can make a further reduction to the case where the module is just irreducible. Make further reduction. The case where B is irreducible. Okay, now that doesn't mean that there's only one categorification. Okay, but once you put some further restriction on it, you can in fact say that you have a unique categorification of this type. Okay, the restriction that one has to put on it is that the abelian category corresponds to the weight space. Okay, this is the highest weight space. Okay, so here this is still a dimension n plus 1. Okay, so the highest weight is n. And if I assume that this is simple, is semi-simple, I guess that's what it means there. Okay, then there is a unique such sl2. Okay, so one just has to check theorem B in this one example, and then that proves the theorem. Okay, so there's a number of ways to describe this minimal example. Okay, and I'm going to describe one of them. Okay, so this can be constructed in the following way. Since the degenerate affine Hecke algebra is acting as endomorphisms of powers of our functors, it's not surprising that we can construct this basic example starting with the degenerate affine Hecke algebra. Okay, so remember that this is generated by t's and x's. The x's generate a polynomial subalgebra. And so what I want to do is mod out by the ideal, which is generated by symmetric polynomials with vanishing constant term.
Is that the center of the ring?
So this is an ideal. I mean, as Arun mentioned, the symmetric polynomials in the x's are the center of the algebra. but I'm taking the ones with vanishing constant term and taking the ideal generated by them. Okay, and this is a simple algebra. Okay, this is related to what I said earlier. We want to make the x's act nilpotently. And that's the idea of modding out by this ideal. And we obtain the unique simple module. I mean, this is the algebra over which the unique irreducible module for the degenerate affine Hackett algebra for which the x's act nilpotently factors through. Sorry, the parsing was a bit tough. Okay, but in any case, we take for each I, we can consider the subalgebra where we just take the generators from 1 to I and just see what its image in this quotient is. Okay, so we call this image H, I, N bar. Okay, and this is turns out to be a finite dimensional, I guess it's clearly finite dimensional symmetric algebra. Symmetric in the sense of what Meinhof-Geff talked about. It's equipped with the non-degenerate trace form. Okay, with a unique irreducible module. Okay, you see we're taking, this is going to factor through some cyclotomic quotient of this affine Hackett algebra. So really this could also be thought of as a block of some cyclotomic Hackett degenerate cyclotomic Hackett algebra. Okay, and now we just build using these algebras, okay, which are included one in the other, a sl2 categorification. So we set A to be the direct sum of the module categories. Okay, and since we have this sequence of inclusions, we use induction and restriction functors. Okay, form an sl2. Okay, and the action of the degenerate affine Hackett algebras, which we need in the definition of the sl2 categorification, are just evident somehow from the. For example, if we restrict from hi to hi minus 1, we have the leftover xi, which can be used as an action for that restriction. So the actions of the endomorphisms x and t are just evident in this construction. Okay, so working directly in this particular model of this categorification for an irreducible module, one just makes the calculation of Ricard's functor directly and shows that you get the appropriate result, this theorem B. Let me just quickly mention, perhaps without writing, that this is related to geometry by the following fact, that these algebras are matrix algebras over cohomology rings of Grassmannians. So we take the Grassmannian of I-dimensional subspaces of an n-dimensional space. Okay, so we could just as well replace the module category for these algebras by the module categories over these cohomology rings. Okay, and one can then construct this categorification in a geometric way using correspondences. Okay, but I won't say much more about that. Okay, instead, I want to go back to the comment I made earlier that when you restrict, so we filtered our categorification in a way such that on each subquotient we get not really a derived equivalence, but just something like a Morita equivalence, an equivalence of abelian categories, which has just been shifted in various degrees. And so one can try to axiomatize this kind of equivalence of derived categories. And let me just explain how one might do that. So suppose we have two abelian categories, A and B. Okay, then we say that an equivalence of the derived categories is called perverse. Okay, if we have filtrations of each of the abelian categories, okay, together with a function which you should think of as being assigning an integer to each level of the filtration. Okay, and we require that first we get a restriction to certain subcategories. Okay, so I'm going to use Pramod's notation here. So he put subscripts like, for example, C for constructible to mean that the homology of the complex should be inside that subcategory of constructible sheaves. So I do the same thing here. This means the full subcategory of complexes for which the cohomology is an object of the subcategory AI. So taking these subcategories, I want them to match on the two sides. Okay, and secondly, I want to say that up to shift, we get an equivalence between quotients of the filtrations. So I suppose I should say that these are Serre subcategories. Okay, let me just be more precise about what I mean by this last statement here. So we have some equivalence of these. Okay, we have some equivalence F. Okay, and it restricts to an equivalence of these subcategories. Okay, now these, by the way it's defined, these are automatically nice subcategories. They're closed under triangles, in the sense that if you have a triangle with two objects in that subcategory, then the third one will be there as well. That follows from the Long-Zach, the snake lemma. And they're also closed under taking direct summands. Okay. And these are exactly the type of subcategories for which you can form triangulated quotients. Okay, so we can form quotient by these subcategories and get an equivalence of triangulated categories. Okay, now the abelian category A is embedded into its derived category. Okay, and of course, once the homology is concentrated in degree 0, then to get this embedding, we need to mod out by a I minus 1. Okay, and now I can further restrict to just considering AI. Okay, so this thing embeds into there, and similarly. So the question is, when I push this abelian category into this triangulated category, how does it compare with this one? Okay, and this statement here means that this doesn't do the job of matching these up, but as long as we shift by this amount, then we do identify these subcategories. Okay, and well, of course, the reason I stated this is because the equivalence which shows up in the sl2 categorification setting is one of these perverse equivalences. So, if okay, the functor that we constructed is perverse. Okay, with respect to the following filtrations, we can make a filtration based on how many times we have to apply the functor E to kill an object. Okay, and we can do the same thing with F. Okay, and so the statement is that with these filtrations, we get a perverse equivalence where the shift is 1 minus I. So it's kind of a surprising result, because what you get, therefore, are equivalences between various different quotients of the category. So for example, if we consider representations of the symmetric groups, then we get certain quotients of that category, okay, which on the face of it are, I mean, one is sort of given by restriction, the other by induction. So the relationship is not so clear. And the last comment I want to make is that if you're given some abelian category A together with the filtration and together with this function P, then the category B is unique if it exists. Okay, so somehow from just the information of A with this filtration and this combinatorial data, one gets, at least in certain good situations, one gets this new abelian category. Okay, and so in this way, for example, in the case of the symmetric groups, if you take a block with some defect group, you can get to any other block of the same defect group by a sequence of these thetas. Okay, but each of these thetas can in principle be affected by a certain combinatorial type equivalence, okay, for which you can actually write down, you can construct some kind of, what should I say, progenitors in the sense of Ricard's Morita theory for drive categories. And this combinatorial data, these filtrations and this P are encoded in the crystal graph of the Kac-Moody algebra. So somehow that one gets the feeling that one can do a kind of bootstrap process where one starts with certain blocks that one knows very well, for example, these special blocks called the Rouquier blocks, and then make one's way via these nice combinatorial type equivalences to all the other blocks. Okay, thanks.
Don't limit the speaker again.